This is the screencast for section 4.6, example 10. We're going to work on a word problem for damped oscillation, specifically a damped oscillating spring. I don't know if you've ever watched, well, pretty much anything bounce, but a spring will have a good bounce at first, and then it will, eventually slow down its bounce or its stretching. That is an oscillating spring. That spring will move back and forth, but its amplitude or the length that it stretches lessens and lessens and lessens, so it is damped. Now this specific problem says Dr. Sanchez's physics class collected data for an Airtable glider that oscillates between two springs. The class determined from the data that the equation that modeled the displacement of y of a spring from its original position as a function of time t. Identify the damping factor and tell where the damping occurs. So from the previous example, example 9, the damping factor is going to be the function out in front. Damping factor is 0.22e to the negative 0.065t. Now I know that that is exponential decay, so I am going to guess that the oscillation is going to happen as x approaches positive infinity. And from the image you can see the damped oscillation, the damping will occur. Damping occurs as x approaches infinity. Now part B asks approximately how long does it take for the spring to be damped so that the y values are between negative 0.1 and 0.1. Well, I chose, because it's hard to see on their picture where 0.1 exactly is. I can get a good idea, but not exact. So I chose to graph this with the same window they used. Well, very similar. And then in y2 and y3, I graphed y equals negative 0.1 and positive 0.1. So now I can visually see where this graph is going to start, the damping is going to take the y values between negative 0.1 and 0.1. So here they're way too big, but then they start getting smaller and smaller and smaller. So I found this value here as a minimum, and that's actually still a little bit lower than negative 0.1. So I went a little bit after that. And I've just decided that, and then I'm sorry, I found the next maximum, which is in fact lower than 0.1. So I'm going to state that anytime after 11.97, is it seconds? Well, it's a glider, so I'm going to guess seconds. It doesn't really say, does it? Okay, so we'll say seconds. Anytime after 11.97 seconds. Now this number is not going to be exact. I understand that, the book understands that. It is to the point where you cannot mention a number where the next oscillation exceeds the boundary. So if you said 11.97, you're fine. If you said 11 or 12.01, you'd be fine. 13.07 is a little too late because the previous oscillation, the previous values were all between 0.01 or negative 0.1 and 0.1. So sometime after 11.97 is a good approximation. The now try problem, number 71, also talks about an oscillating spring whose oscillation are modeled by this equation here. So I've done part A and I've graphed this ahead of time. I've graphed y and it's two damping curves. So I graphed the positive version and the negative version of that little function out front so you can see them dampening the original function. And it wanted me to graph t between 0 and 12, so that is what I did. My x-min was 0, my x-max was 12. That was all in part A. Part B. Approximately how long does it take for the spring to be damped so that the y values go between negative 0.2 and positive 0.2? Well, the strategy of, I adjusted the window a little bit so I could see better, but I graphed in y2 and y3, y equals negative 0.2 and y equals positive 0.2. So I can see this first oscillation is actually within the boundaries I need it to be. I found that pretty much any time after 1.5 seconds, we'll go with 1.53 seconds, my y values will stay between